Thank you so much. Thank you. It's really fun being here after a while. I did my PhD here since my homecoming. So what I wanted to do today is precisely what Jesus mentioned. I want to talk a little bit about this new stability notion for foliations or adjoint foliated structures. I've tried to make the talk as less technical as possible, but I apologize if there's technical parts. But if you don't understand something or if something is not clear, please do ask them. So the first thing I want to talk about is what case stability is. So case stability, by now a pretty well-established theory. It was discovered or described by Tian in the 90s, and then by Simon Donaldson in the early 2000s. And the idea here was to find a stability notion which would predict which Fano manifolds admit something called the Kähler-Einstein metric. For us, the metric side is not really important today, but Fano manifolds are. So Fano variety in general, for me, is a projective variety with an anticanonical ample divisor Kx. So if you don't have intuition for this, you can also think of these varieties as kind of like generalizations of the sphere in higher dimensions due to like positivity of the Ricci curvature. So it was a big problem in the 90s after the solution of the Calabi-Yau conjecture to try to find these Kähler-Einstein metrics. And it turns out the right theory is this case stability theory, which was first defined by Tian and then by Donaldson, using something called a test configuration. So test configuration is a one-parameter family with some extra conditions. It has a GM action on the family, and you can think of like a GM equivariant isomorphism of the general fiber with our target variety X. And we usually want to imbue some kind of polarization L, so some kind of ample line bundle. So here as well. Usually for Fano varieties, it's just going to be the ample line one. So we get some kind of GM equivariant isomorphism between this and then the general fiber. Okay, roughly. And then the way we define this case stability theory is by using something called the Donaldson-Futaiki invariant of each test configuration, which I won't define. I don't think it's important. But the case stability really relies on the positivity properties of these invariants. Okay, so if it's greater or equal than 0 for all test configurations, we're going to say it's case semi-stable. And if it's greater than 0, we're going to say it's case stable. And there's also a class of k-polystable Fano varieties play an important role in the construction of moduli spaces. So Patricio, thankfully, talked a lot about the idea of like moduli spaces and the idea of like we have this idea of like between catalogs and books. So in the case of Fano varieties, if you want to create a moduli problem, this case stability theory is telling you what the catalogs and what the books essentially in each catalog should be. Okay. And this theory is fairly recent. I mean, I think like from 2014 up until now, it's being constantly developed. So what it gives is a projective moduli space, which usually is denoted this way. They're not important, which parameterizes these k-polystable Fano varieties. Okay, this is even a little bit more stronger than what Patricia was talking about in the previous talk, because you don't just necessarily want compact here. You actually get projectivity of this moduli space, which is a really powerful and important property. And the way we went from this description of the Donaldson-Futaiki invariant test configurations to the construction of a projective moduli space was by the introduction of birational geometric techniques to study this case stability notion. So this Donaldson-Futaiki invariant approach and the first via test configurations doesn't allow us to do this, but there were some seminal results in the past 10 years that have allowed us to go from this more analytic definition of this algebra geometric, but more analytic in mentality definition of case stability to a more birational geometric definition of case stability. So there's a few results. The one is by Liu and Shu in 2014, which shows that there's a reduction to special test configurations. And special test configurations are important because the central fiber of the special test configuration is always irreducible, which is not necessarily true for any test configuration. And then there's a very famous birational geometric criterion by Fujita and Lee, and around 2017, which gives something called the beta invariant, which is only birational geometric, so it really relies on only divisors, which Patricia also answered a lot about, which I'm very thankful for. But these two things, and then some other results that allows to prove projectivity by Shu et al. Shu and his collaborators worked a lot on these kind of problems. They rely on a very fundamental theory in birational geometry called the minimal model program. So the minimal model program, heuristically, is you can think of it as a sequence of surgery operations, like starting with any variety and leading to some classes of varieties that lead to what is called a birational classification. So the birational classification is kind of like this classification based on surgery. But this MMP is not very trivial that it exists. Actually, it's a very big result by Birkar, Cassini, Hakon, McKernan in 2010 that says that this exists and terminates. It's probably not important for you. For some cases. And then another really important result, two actually important results by Birkar in 2018 and 2019 is the solution of the BAB conjecture and the boundedness of complements. So in fact, Kosher got the Fields Medal for the BAB conjecture solution. So this BAB conjecture, all it says is that if you take all these Fano varieties, the set of them with some prescribed singularities, which play an important role in this MMP, let's say MMP here, all it says is that you can find they're bounded. And what bounded means is you can find a finite number of families that you can put them all as general fibers. So there's some kind of like bound for these Fano varieties. And this is a really important. In parallel, and maybe I should also mention some results by Hakon, McKenna, and Shu, and Kolar for more general things on the moduli side. But anyway, in parallel, a lot of people were interested in what's called foliation. So what they wanted to do, they wanted to construct some MMP theory for foliations. So I'll explain foliations in a second. What I will say about this MMP for foliations is that's really, really hard, and it probably fails in many, many points. But the reason why someone would want to study foliation, so what is a foliation? If I take a projective variety, X, and I take a saturated subbundle of the tangent bundle, so it's like like some kind of T of F usually, that's how it's denoted, of the tangent bundle of X, this is going to be called a foliation. Okay. Heuristically, you can think of this foliation as kind of a way to encode differential equation data on a manifold. So if I was in A2, for instance, you can think of any foliation as kind of a linear combination of polynomials based on like the multiplying the partials. Okay. So in a way, it gives me some kind of data of differential equations on the manifold. Here in A2, it's more simple, but obviously I can keep doing this for any manifold or any variety I want to. So a lot of people were interested in this kind of thing, ideally because they wanted to describe things from this MMP of the foliation side in order to feed it back to the MMP of variety side, but also because they're interested in this classification of foliations in terms of like differential equations on varieties, but also because the key object we'll be talking about today, which is algebraically integrable foliations, which are foliations that have algebraic leaves, are induced by some kind of rational map. Okay, so some kind of rational map like this between two varieties. And for birational geometries, it's really important. Rational maps take a really central stage in the study of birational geometry. So obtaining some kind of classification theory for these things becomes really important.
Yes, one question.
Yeah.
Simple. What does saturated mean? I suspect it's important.
It's like the Lie bracket thing works well.
Except the Lie bracket.
Yeah, exactly. Yeah. You can actually drop the saturation thing and you can still consider foliations, but then things become horrific. Like you cannot do much about them. So usually, like even if you drop the algebraically integrable thing.
Oh yeah, what's that?
So this means that the leaves are algebraic, but you can think of it as like induced by a rational map between two varieties. And like the different dimension difference is going to be the rank of the foliation. And we really care about this. We don't have any results, like very few results on the MMP of non-algebraically integral things. So here, I mentioned before that the MMP techniques are lacking, but very recently, due to two papers by Cassini, Hang, Yu, Mang, Spicer, Spaldi, and Xia in 2025 and 2026. Now we know that we have BCHM 10, so this result, and the BAP conjecture equivalence. For some specific objects, which are called adjoint foliated structures, which is precisely what we're going to talk about today. So what are adjoint foliated structures? Well, these people realized very quickly that foliations, they serve a lot of pathology in birational geometry. They're not bounded for sure, they have a lot of problems. Even if you're still algebraically integrable, there's still a lot of problems. So the idea was, okay, instead of like just looking at the foliation, let's look at a triple where X is the variety, F is the foliation, and T is a rational number between 0 and 1. And let's kind of look at a joint of the geometry of these things by looking at some adjoint canonical divisor. So we're considering this adjoint canonical divisor. And we try to interplay between the geometry of the variety and the foliation. So for those of you who are doing birational geometry, this kind of mimics the idea of log Fano pairs, but it's not exactly that. So if you think about it, when I go closer to T, I'm looking at just the geometry of the foliation. If I go closer to 0, I'm just looking at the geometry of the variety. I'm just dividing the coefficient T. And the question is, now that we have these two key results that prove many things in the case stability for Fano varieties, whether we can A, define a case stability theory, and B, and more ambitiously, obtain some moduli problem, some moduli space for in the Fano case. So for what is called adjoint Fano foliated structures, in which case this divisor, which I usually denote this way, the adjoint, the anti-canonical divisor, the anti-canonical adjoint divisor, sorry, is ample. So this is the final condition here. And the answer is yes. So that's the content of the talk today, essentially. So yes, definitely yes for A, and progressively yes for B. Like we have a bunch of results for B. So for A, the definition, you can do two things. You can either define it by rational geometric, but if you do it this way, you're going to run into problems trying to construct your moduli theories. And you can try to define it using this Donaldson-Pataki invariant test configuration normalism. But then you run into other problems because you have to prove a lot of things. But this is probably the right idea in order to define the case stability of foliations. So here you only have to do a modification. You now consider test configuration This is this thing.
So in all this idea, would you say the moduli space by adjoint foliation, you're fixing X?
No, X varies.
So the pair is good. You are
I
adjoint.
didn't want to erase it.
Don't erase it.
Say again?
So it's for the pairs, X.
Yeah,
and then
exactly.
You are varying.
Like you can think of it this way: you have a moduli space that will vary X and the foliations inside of X. You have to, otherwise. You can also kind of look at only fixing X and then varying the foliation, but you wouldn't get many interesting things because you would also want to see the generations of the foliation in other varieties. Which if you fix X, you're not going to be able to.
And could you give like a simple example? One dimension or something? That's two dimension.
And in one dimension, it's not going to be interesting, right? Like, what's going to be the interest in one dimension? Like here, you can even plot it, and you can see like the vector directions. They're going to be the leaves of the foliation.
So those leaves is what gets contracted. The directions of those leaves on X get contracted and give you the rational map. The rational map of what?
Yeah. Exactly. Yeah. So for this, you take X a test configuration, but you also put a foliated part, and you also have the line bundle again over A1. And the main difference is you ask for f of X to live in the relative tangent sheaf and be an algebraically integrable foliation. So all this is saying is take a generation of your foliation, but in a way that everything keeps algebraically integrable. Okay? And then you can define the K-stability notion in a similar way by defining a Donaldson-Futaki variant for the test configuration and asking for its positivity. And here, the important thing is you also have to rely on T. So this is based on the T as well. So what can you do using this definition? In a way, it may not be so natural because it's the definition of like the original definition of like Donaldson-Futaki invariants and all these things was created to construct to prove that there's existence of metrics. But here, you can ask questions about metrics, but the motivation is the moduli theory. So you really want to reduce to this birational geometric theory I mentioned before. So how do you do that? Well, the first thing you can actually show is that this K-stability notion actually gives good results in terms of the singularities of this foliation. So if this X F T is K semi-stable, then the pair, well, this XFT is log canonical. And here the important thing is I'm not restricting just to the Fano case. I'm doing it for any projective variety with any foliation, and because I get defined as Donaldson-Futaki invariant, and I can get this result, which is mimicking Odaka's result. And the second one, which is even stronger, is that if this is a Calabi-Yau, so let me write it this way. So if XFT is Calabi-Yau log canonical, it is K semi-stable. And if it is KLT, it is K stable. The second one is that if this is general type, so meaning the adjoint canonical divisor is ample and log canonical is always K stable. And the third one is that if it is Fano and K semi-stable, it will be KLT. And okay, if you're not familiar with all these like KLT log canonical things, just think of it as it gives a very good restriction of the singularities of the things you're considering in order to run these results from these two papers. Okay. So running this, you can get the equivalent of Lee and Shu's reduction to special test configurations. So a bit more formally, so for adjoint unaffiliated structures, it suffices to only look at special test configurations or F compatible test configurations to denote that we're in the foliated setting. And the other important thing is that there exists a birational invariant for the foliation capturing case stability. So essentially, what is written here on the board is precisely the two main results I mentioned before for the case stability of final variables. That you have you can reduce this to special test configurations, and then you can construct some birational invariants. So this beta invariant or delta invariant, which is capturing case stability. And this is actually non-trivial. You have, in order to prove this, you have to define another stability notion called Ding stability, and work through that in order to show some equivalence and show that you can reduce this birational distortion. Any questions?
What does it mean to be non-canonical consolidation?
Good question. So it's not like exactly like the log Fano pair. It looks kind of like this, but you have some kind of adjoint foliated log discrepancy term, which looks like this, where you have the usual log discrepancy by multiplied by 1 minus t, and then you have something called the foliated log discrepancy of this divisor. You can think of like this divisor has a canonical bundle, and then you take the usual decomposition. But the important thing is that this foliated
divisor is an X.
Huh?
It's a divisor an X.
overrides.
Over it.
Yeah.
Yeah. Okay, sure.
Yeah. And the important thing is that this AF of D is the usual discrepancy term, but you add this epsilon term, which is not always one. It's why this entire theory is not equivalent to the log Fano pairs, for instance. Like this epsilon of F is either 1 or 0. It's 1 if it's transverse, so it doesn't meet the foliation. It's 0 if it's invariant. And that plays a really important key part. And log canonicity is the usual way, like you have the usual positivity criteria. So you're looking at the log canonicity, not just the variety, but just the foliations. But actually, that result is really important because what was it? This one, it's KL. The foliated thing is KLT, but also the variety is not necessarily KLT, but it's potentially KLT. So you find a divisor to make the pair KLT. And that is really important in order to use these results. For the MMP, you need to be able to control the singularities in order to be able to run the program. And if we didn't have that, we wouldn't be able to run the program. Okay. So, where was I? Okay. So using this, you can prove boundedness. So the set of Fano case semi-stable adjoint foliated structures is bounded. And this is the very first key step that is telling you that you can potentially do some kind of moduli theory. This boundedness is telling you that you can create families so that you can contain all the fibers of variety and foliation at the same time. And it comes from this BAB conjecture picture for the adjoint foliated structure. So this is the first step, and the second step, well, probably the third step really, is to verify what is called the criteria of S completeness and theta reductivity. So what you can show is that the moduli problem of case semi-stable adjoint Fano foliated structures satisfies the validated criteria of S completeness and theta relativity. And this is pretty important. I mean, these are necessary criteria to show that you have the existence of this moduli space that we mentioned before. It's in Alpert's terminology, the idea of like a good moduli space of a Deligne Mumford stack. Here, you also kind of use the MMP techniques with actually the Donaldson-Futaki formalism and the Ding formalism we mentioned before. But the important corollary for this is the following. So if I have something like this, which is a polystable, then the automorphism group of X, really, you should think about like fixing this foliation is whatever. Okay, and this is a key component. These so these moduli spaces, this theory of good moduli spaces is generalizing GIT in a way where you can think of every closed point having reductive stabilizers. And so the closed points here are the K polystable points, and the stabilizers have to be reductive. Similarly,
Is that larger or smaller than automorphism?
I mean, it has to be small. It's also fixing.
Oh, it's fixing.
So. And yeah, and also like if this is a K stable, then this automorphism group is actually finite. So these results of this part of the board, what they tell you is you should expect a good moduli theory to hold here, barring some conditions, which I'll talk about in a second. But the boundedness and this thing, I mean, here already, this tells you that you should probably get some kind of Deligne Mumford stack for K stable. Huh?
5 minutes, 3 minutes.
Okay. 3 minutes ago.
I got.
Okay, so let me just finish. So one final thing, and the other corollary is that the K polystable degenerations are unique. And let me just finish by saying that the next step for constructing the moduli theory is to show a property called openness, which is a bit out of reach because it needs this boundedness of complements result I mentioned before, which is not available yet in this foliated setting, although we expect we'll have something positive in some time. I think we're working on it. But the one other thing we really need right now is to find examples. So we need to construct a theory that will give us the ability to find examples of these things. These things, we only have very few of them. But I just came up with in the paper where I defined this notion, where I just wanted to see if it works well or not. The third thing, sorry, I'm over time right now. But the final thing is, one would be also tempted to go to the limit where if we go to t equals 1, for instance, where we only look at the foliation and nothing else, but then we know that this stability notion is actually vacuous. It doesn't tell us anything. That you can always find a divisor that destabilizes, that induces a special test configuration that destabilizes the balance of Papazachariou, right? So here in the foliations, we just looking at the foliation geometry, we know that we have a lot of pathologies from the MMP, even from this theory. So it seems that this kind of combination of the two geometries of the variety of the foliation is probably the right way to look at this. Yeah, let me finish it.
Any questions?
Yeah, of course. I mean, you can define it exactly the same way. We're actually working to see if the minimizers, like they play the same role, which we think it should be the same. But yeah, you can define it because you just define it as like the usual product. You have to be a little bit more careful when you define the volume of the, but you still have like the idea of like a volume of valuation. Usually you just want to be a bit centered in the foliation in some kind of way, but you can define it absolutely.
Could you say a bit more about the proof of this evaluative criteria that's the biggest feature?
Yeah, so this is the hardest one. Okay, so the way this works, I'll talk a little bit only about S completeness because it's kind of repeated. But the way that S completeness works, or at least what you want to show, is if you took two families over some DVR. Sorry, this is going to be technical, but you asked for this. So let's say I have two families, okay, over the DVR. These two families, I want them in this case to have equal isomorphic generic values, and obviously, like also isomorphic foliations in some kind of way. Okay, and what I want to know is, I mean, there's a very canonical way where I can glue these things together to get a two-parameter family. So, but the two-parameter family has to be done away from the central locus. So if I do this, I can get like a third family. Let's call it just X, just Fx, over some kind of thing, some kind of stack equation, doesn't matter. And then I want to know if I can fill this in.
Exactly. Separating
The question. Someone telling me I'm doing the wrong thing. So the way you do this is by really looking at the generations, and like the key component actually in this extension is you really want some finite generation property. Okay, so you want to take the product of some kind of ring that's finitely generated, and the only way you can do this is using least square. So because there's not, like, honestly, there's no other way to show finite generation in biaxial. So the way you do it is by using Ding invariants and extracting particular divisors that take you upstairs and show you can have some kind of finite generation. And then you can uniquely fill in this family. This is maybe X0. You get like some unique fill to this STR. And precisely this is what gives you but you need to have the finite generation, and then you also have to take the bonds with Fleck invariance to make sure that all the fibers are going to be case sensitive, because you need to land at the same motion. But yeah, it's a fairly technical thing to do.
Okay, thank you. So we're running out of time since Josh asked the last question and he's the next speaker. We're fine. Okay, thank you very much.